Good day and welcome back to the second part of our discussion on the fundamental theorem of line integrals. In the previous video, we introduced the concept of the fundamental theorem of line integrals, investigated a simple example, and made several observations. So let me begin with the reminder. If we have a curve C given by a vector-valued function r of t, and the parameter varies from a to b, then the line integral over this curve C of a conservative vector field. Remember, a vector field is conservative if it is a gradient. So i.e. f is conservative is equal to, by the fundamental theorem of line integrals, the potential function for that vector field, little f, evaluated at the finish point, minus the potential function little f evaluated at the starting point. And it's worth noting that in order for us to effectively apply the fundamental theorem of line integrals, there's really kind of two big pieces of information we need to first think about. One, is the vector field we are integrating over conservative? It's not always the case that we will immediately be told that we have a conservative vector field. We might first have to verify that fact. Secondly, if it is conservative, how do we go about finding this potential function little f? Something we talked about in one of our previous sections. And before diving into such an example, let me note that if we have a two-dimensional vector field with component functions p and q respectively, the line integral over that vector field is equal to the line integral of p dx plus q dy. That is to say, we have this nice connection back to our previous material with line integrals. Let's now explore an example. And note this example has really two parts to it. The first part is find a function little f so that the given vector field is the gradient of f. And then once we find that function little f, we'll go ahead and use it to evaluate a line integral. Note that for the first part of this question, in order to determine this function little f we would like to find, we need the first entry of the gradient vector to be the partial with respect to x, and the second to be the partial with respect to y. So what we are being asked is to find a function, f of xy, with the partial of f with respect to x, 3 plus 2xy, and the partial with respect to y is x squared minus 3y squared. And in order to find a function f which satisfies both of these equations, we need to undo these partial derivatives and match up our two possibilities. So from this first partial with respect to x, we know that f can be represented as the antiderivative of 3 plus 2xy with respect to x. And when we antidifferentiate with respect to x, we treat the y's as constants. 3x plus x squared y is an indefinite integral, so plus a constant. But recall from our previous discussion that constant can involve y's as well as true constants. Similarly, we get a second representation of f, which is necessary to make sure we can determine f up to more than just any quantity involving y's. So f is also the antiderivative of x squared minus 3y squared with respect to y, which means we treat the x squared as a constant. And because it's an indefinite integral, we have plus c, but note c is a quantity that could involve x's. And the idea is that once we have these two representations of f, we should be able to match them together to get a single function representing f. And the general rule of thumb is any quantity involving both x's and y's should appear in both of the equations. If there's a quantity involving x and y's that only appears in one equation, double check your work. That would indicate the vector field is not conservative. So we write that quantity down, and then anything else is going to have to be accounted for as a constant only involving x's, so we'll say plus 3x, or a constant only involving y's. And once we've determined this representation of f, note that if you are unsure if we've done this correctly, you can always calculate two quick partials and verify that we have. And now that we have found this function f, we're going to go ahead and use it to answer the second part, which involves evaluating a line integral. And the observation that I would like to make is that the 3 plus 2xy is the first component of our vector field, and x squared minus 3y squared is the second component of our vector field. That is, we can think of this as having the form p dx plus q dy. And note from our initial observation above, a line integral of the form p dx plus q dy can really be thought of as a line integral over that vector field determined by p and q. That is to say, this is the line integral over the vector field given by the gradient of f. And note, whenever we see a line integral of this form, this is where we can apply the fundamental theorem of line integrals. It's a conservative vector field. So note, we haven't mentioned anything about the curve C, and the reason being, the curve C is completely irrelevant to evaluate this line integral. We only need to know where the curve starts and where the curve finishes. So if we apply the fundamental theorem of line integrals, and whenever we use the fundamental theorem of line integrals, you need to somehow indicate to me that you're doing so. And I believe the simplest possible way is to simply write ftoli over that equal sign. And the fundamental theorem of line integrals tells us we get the potential function little f evaluated at the end point of the curve minus that potential function little f evaluated at the starting point. And if we substitute into the function above, x is 2 and y is 1. We have 2 squared times 1 plus 6 minus 1 minus f of 1 comma 0. So if y is 0 and x is 1, all we're subtracting away is a 3. And this all combines together to give us our solution. And let me note that the wording of this problem is very generous, in the sense that it first asks you to find this potential function little f. If we were instead only given this line integral to evaluate, it now has to be part of our thought process to check, is this a conservative vector field? And at the end of section 16.1, when we are introducing vector fields, we spend a little time talking about conservative or gradient vector fields. And let's just go back to a question similar to what we explored there. Is a given vector field conservative? This is something we need to be able to answer. And it turns out that we had a simple way of checking. So let me remind you, if we think of these components of the vector field as being p and q, we can know p is equal to e to the x cosine y, q is equal to e to the x sine y. And note, if we have a conservative vector field, we would want the first entry to be the partial little f sub x, and the second entry to be the partial little f sub y. And if f sub x is equal to p and f sub y is equal to q, then note fxy and fyx, the two mixed partials, should be equal to each other. And note f sub xy would be p sub y, and f sub yx would be q sub x. And if those quantities are equal, that gives us a good idea, or at least a reasonable bit of intuition, that the vector field would be conservative. In this case, when we take the partial with respect to y of p and the partial with respect to x of q, they differ by a negative sign, so they are not equal. And since they are not equal, that would imply that these mixed partials are not equal, so such a function could not possibly exist. So not conservative because the partials p sub y and q sub x do not match up with each other. In general, if we have a conservative vector field, using the argument we've made above in red, that would imply that py is equal to q sub x. And whenever we see an if-then statement, we do have to be careful. The order of an if-then statement is very important. And typically, if we were to discuss such a thing in class, I would give several silly statements to really illustrate the importance of the order of a if-then statement. So consider the following statement. If it rains tomorrow, then I will wear my rain boots. If I show up to teach class tomorrow, hypothetically here, and I am wearing my rain boots, can I go backwards from this if-then statement to make the conclusion that it has rained? And the answer is no, I just might really like my rain boots. Now, maybe a more relatable sports analogy here would be if the Packers win the Super Bowl, then they won the last regular season game of the year. If we turn that statement around and say, if the Packers win their last regular season game of the year, then they win the Super Bowl. That is a completely ridiculous statement because, of course, they could win their final game of the season but not make the playoffs. So we have to be very careful with if-then statements. And this leads us to the following question. If we know this relationship holds true with the partials, that is p sub y equals q sub x, can we make the conclusion that the associated vector field is conservative? This is the exact thing we were mentioning we need to be careful about. And it turns out that the answer is yes, but I'm going to add in here under some reasonable restrictions. And there are times when it is useful for us to go through details related to these restrictions. Here I'll note that if you look in the book, you can see a more full explanation. You need to be in what's called a simply connected domain. That would be one single piece with no holes in it. But for us, that's not really going to be an issue that we have to be concerned about. So we will say that if those partials are equal, we will make the assumption that the associated vector field is conservative with the full realization that there are some restrictions that do apply. So we will continue this discussion in our next video. Stay tuned and take care.